In this video, we're going to talk about the sinusoidal nature of the induced electromotive force. So let's assume that we have a coil that is placed in the presence of a magnetic field that is pointing in this direction. So we assume here that the coil is rotating in the counterclockwise direction. So at this instant, we notice that the normal vector to the coil makes an angle of theta with respect to the direction of the magnetic field. So notice that this loop has n turns of wires. So we can go ahead and calculate the magnetic flux as given by this quantity right here. So we want to notice that because this angle is changing, so I can replace theta with omega times t, where omega is the angular speed. So now, since we know what the magnetic flux is, I can use Faraday's law of electromagnetic induction to calculate the induced EMF in this coil. So this is just equal to negative n times the derivative of the magnetic flux with respect to time. So n here is just the number of turns that I have in this loop, and when I take the derivative of this function, I end up with this function right here. So again, you can see that this function is just a sinusoidal function. So if we plot this function, or if we plot the electromotive force on the graph, we notice that it's going to look like a sine curve with some maximum right here, and this maximum can be calculated as n, the number of turns, times the strength of the magnetic field, times the cross-sectional area of the loop, times omega, where omega is just the angular speed. Now let's look at this example here. So this is example number 30.7, and in this example we're going to calculate the EMF induced in a generator. So suppose that we have an AC generator that consists of 8 turns of wire, each of area A given by 0.090 meters square, and the total resistance of the wire is 12.0 ohms. And then it says that the coil rotates in a 0.50 Tesla magnetic field at a constant frequency of 60.0 hertz. Find the maximum induced EMF in the coil. So in this example, so this is an example of an AC generator. I think if you remember from the previous video, we said that what is really unique about the AC generator is that it uses these slip rings. So there are 2 slip rings that are attached to these brushes, and with these we can make a connection to some external circuit. So basically what happens is that whenever this loop rotates through 180 degrees, the direction of the current is going to change. So in the first cycle, the current enters from this brush and leaves from this brush here, and then in the second cycle it enters from this brush and leaves through this brush right here. So the current is going to change directions back and forth, and that way it can generate an AC voltage that looks like this. So what we know that we can calculate the maximum value of the induced voltage using this equation here. So it's just the number of turns times the strength of the magnetic field times the cross-sectional area times omega. Now we know that omega can be expressed in terms of the frequency using this equation right here. It's just 2 pi times the frequency. So if I plug in those numbers here, I end up with 136 volt. So this is the maximum value of the induced EMF, 136 volt. Now in part B, it's going to ask me to calculate the maximum induced current in the coil when the output terminals are connected to a low resistance conductor. So again, I can calculate my Imax, so using Ohm's law. So Ohm's law tells me that Imax is equal to Emax over R, and we know that the total resistance in the coil is 12.0 ohms. So if I substitute that, I get an Imax of 11.3 amps. All right. So now, just very briefly here, so we'll just talk about one application of electromagnetic induction. And so electromagnetic induction play a key role in electric motors and electric generators. Now, an electric motor is a device that converts electrical energy into mechanical energy, and this would use a magnetic field. So the picture that you see here on the right explains the principle of operation of an electric motor. So basically, the way this works is that you have a power supply. So this is my battery, this is my positive, this is my negative here. Now the current, as the current is going to go through this loop. So notice that the current on the left side of the loop here is pointing up. Meanwhile, the current on the right side is pointing down. Now, because this is the north, so this loop is placed in the presence of a uniform magnetic field, and this is the north and this is the south. So since we know that the magnetic field lines always point from north to south, it means that this vector here tells me the direction of the B field. And so if I know what the direction of the current is and what the direction of the B field is, I can calculate the force on this loop. So notice that on the left side, so on the left portion of the loop, because the current is going up and the magnetic field is pointing in the, so we can say that the current is in the J direction and the magnetic field is in the I direction. So I can calculate the direction of the force by doing J, so J hat cross I hat, and we know that J hat cross I hat is negative K hat. So negative K hat means that the force is pointing into the paper at this point right here. Now on the right side of the loop, the current is going down. So because the current is going down and the magnetic field is pointing in the I direction, if you take the cross product, you get a force that is pointing out of the paper. So whenever you have two forces acting on different points, so in this case you have two forces that have the same magnitude, but the difference is that the point of application of the two forces is different. So one force is applied to the left portion of the loop, the other force is applied to the right portion of the loop. So these two forces are going to generate a torque that is going to cause this loop to rotate in a clockwise direction. So we can see that. So here, so basically, an electric motor. So we're taking electrical energy and converting that energy into mechanical energy. So we can think about some devices, some appliances that use electric motors. You can think about things like a fan, or maybe something like the washing machine and stuff like that. So all those devices uses the principle of electromagnetic induction to convert electrical energy into mechanical energy. Now, an electric generator is simply the opposite of an electric motor. So while an electric motor converts electrical energy into mechanical energy, an electric generator converts mechanical energy into electrical energy. So the principle is pretty much about the same. So again, it uses the principle of electromagnetic induction. So this is an example here of of an electric generator. So in this example, this is a wind, this is a wind turbine. So as the wind is going to push against the blades of this, so this is the wind. As the wind is going to push against the blades, it's going to cause this to rotate. And as this is rotating, it has mechanical energy, but this is designed in such a way that the blades are connected to a spinning shaft attached to magnets, and the magnets spin around a conductive coil, therefore inducing electric current in the coil. So again, this is an example where we're taking mechanical energy from the wind and using the principle of electromagnetic induction to convert the mechanical energy into electrical energy. Now this example here, this is just a picture that shows you a typical example of an electric motor. So what this does is that it simply takes electrical energy and convert that energy into mechanical energy using a magnet.